Okay, problem 3. This is the one about the asteroid that just last week came within, well, 27,700 kilometers of Earth's surface. And we want to find, assuming it had negligible kinetic energy, it was very far from Earth. We want to find what speed was when it was at that closest point. So here I'm calling point 2 is our point of closest approach. Point 1 is very far from Earth. So this is, as you might have guessed, an energy problem. Mechanical energy is conserved. Okay, so EMAC equals EMAC at 1 and 2, you could say. So we need to find kinetic and potential energies there. So when two objects are very far away, the potential energy for universal gravitation is 0. And we said in the problem that it has negligible kinetic energy when it's very far from Earth, so that's also 0. So the left-hand side is, well, I guess I should, say U1 plus K1 is the left-hand side, and of course 0 plus 0. Okay, so great. Now for the right-hand side, potential energy at point 2 is going to be, we just use the old universal gravitation potential energy, which is G times mass of the Earth times mass of the asteroid, which is going to be little m, over the distance between them. I'm going to say it's little r. Sorry, the distance between their centers. So remember, r is going to equal what we gave as the closest approach distance, which is 27,700 kilometers, plus the radius of the Earth. So you actually have to add in the radius of the Earth, so you're going to get like, I guess r is going to equal, what is it going to be, 6,371, so it's going to be 3407-ish, and let's do 34.07 times 10 to the 6th meters. Okay, so anyway, that's our potential energy at the point of closest approach, and then our kinetic energy there, we just use the good old 1/2 mv squared. And of course, v is what we want to solve for. So u2 plus k2, of course, and then so negative big G mass of the Earth times mass of the asteroid over that distance between them that we found, plus 1/2 mass of the asteroid v squared. And what you'll get there is, let's see, you bring that over, you cancel, so let me start, let's go to blue, because I like blue. You can cancel the m's there, obviously, and then what you can get is v squared equals 2 big G mass of the Earth over r. So then v equals square root 2 big G me over little r. And as I recall, I want to say the velocity I got was 4.23 or 32. Well, I guess I'll just go ahead and do it. Let's see, square root of 6.67 e negative 11 times 2, right, times 5.97 e 24 divided by, and then 34.07 E6, close parentheses, equals, 4.8. Okay, I guess that's right. Could have sworn, let me make sure, 2, okay, alright. I guess that must be it. So that is 4.8 what? 4.83, I'll go one more. Kilometers per second, for part A. Okay? Part B is basically the same. In fact, it's exactly the same, except now instead of saying it only got down to this distance from the center of the Earth, we're going to take it to where little r, the distance from the asteroid to the center of the Earth, is just the radius of the Earth, because it hits the surface, right? So, and what you get there is v equals square root of 2 big G me over re. And in fact, well, what you get there, I think, is 11 point... Oh, now I got to do the calculator thing again. I can never quite remember. Let's see. Come on. Okay. I'm pretty sure it's 11.2, but let me just double check there. 6.371. Yeah, okay. 11.2 kilometers per second. And this might or might not be a familiar number to you. It might be familiar because it is, in fact, the escape speed for the surface of the Earth. And the reason why is because really this is an escape trajectory run backwards. So remember that for escape speed, the key for escape speed is mechanical energy equals 0, right? And we started here with mechanical energy equals 0, and then we fell in. And that's the nature of conservative forces. The only force we have going here is gravity. And a conservative force, you can basically run time backwards or forwards, and you'll get the same thing happening. So the fact that the asteroid would hit at 11.2 kilometers per second is not a coincidence. It's exactly the same as the Earth's escape speed because, in fact, the physics is the same. I think that means basically almost any asteroid that hits Earth is going to have just about, it's going to be going just about that speed, you know, give or take a few if it had a little bit of kinetic energy. But interesting little fact. Anyway, that is problem 3 for you.